Hi, in this video we will show you how to implement this Murmur hash in Rust using iterators. This Murmur hash is a non-cryptographic hash function that is suitable for some general hash-based lookup table. Its name is based on basic arithmetic operation, multiply and rotate, that are used in the inner loop of the algorithm. We'll be implementing this 64-bit version. Okay, as you can see, there are many implementations on the net in various different languages. Here I found some canonical implementations in C programming language. As you can see, it's very simple function. It is like 40 lines long. And yeah, in the end of the video we will compare how our Rust implementations compare to this in performance. Also, I found this Rust implementation of this hash, and it's a straight port of this canonical implementation. So we will also compare to this function, just to see if the Rust iterators are fast as these simple while loops that we have here. Okay, so we can begin. So the first thing that we'll do is to copy this function into a new empty project and build it and run it to see is it working correctly. Here we also have some test cases so that we can verify that it's working correctly. So I will just copy all this to new project, this, and then I will also copy these test cases here. Yeah, and now we can just run it. Yeah, and we said that every assert is passing, so that means that function is working correctly. And now we can begin this new implementation. We will use the same signature as this function, so I will just copy the signature and I will just add this suffix iter for this because we'll be using iterators. So these first two lines are just the constants that algorithm uses, so we will leave this the same. And then we have these two lines, so I will copy and then explain. So this age value will be returned from our function as a result, so we will return this, and we will mutate this through algorithms. Yeah, as we'll see below. And this is just initial calculation where we just take the length of the slice and multiply with our big constant. Here we are using wrapping functions because we want to let us that it's okay to overflow, and because modular arithmetic is used here. And yeah, and I can also use this in place because I think I will not need this anymore. So I will just here and delete this line like this. Okay, we can see here that a while loop is used, and we have this counter that is incremented by 8. So yeah, in each iteration of the loop 8 bytes are taken, and then this 64-bit integer is constructed from this 8 byte, and after that some arithmetic is performed. As I said, we will use iterators for this, so we'll no need to calculate any of these positions or counters. Iterators will do all of this for us. So we have a great iterator for this that is called chunk exact. So you call on key, as I said, so each chunk will be 8 byte in the size, Okay, so of course the last byte, last chunk will probably not be 8 bytes, so it will not be returned here, but this iterator provides method so that we can also take care of this last chunk that is smaller than 8 bytes. So you have this method, and you have this method reminder that will return this for us. Okay, I'll just this tip feller correct like this. Okay, so next we will process, first we will process these chunks, and then we will process this that is left over. Now we'll loop through chunks and perform arithmetic. Okay, but before we perform arithmetic, we need to construct this 64-bit integer, and to do this we will use method that will convert this integer from bytes. So yeah, so we have this from LA bytes method because we are on a little Indian machine. If you are on Bing Indian machine, there is also Bing Indian version of this function, and this function accepts the static array of 8 bytes, and here this chunks is a slice, so we need to convert this slice to this 8 bytes static array. And to do this, there is a try into method. This method can fail, for example, if this slice is not 8 bytes long, but as we use this chunk exact iterator, I don't see situation how this can fail. So that's why I will use just unwrap here without do some error handling. And now all that is now left is perform this simple arithmetic that must be the same as before as this. All that is left now is to process these leftover bytes. So first we will check if there are any bytes that we need to process. So we can use isEmpty method for this. So yeah, so if it's not empty, then we will do something. So first thing that we will do is we will initialize some static array and initialize it to 0, and then we will copy to this static array, we will copy this leftover bytes. So we will use clone from slice method for this, and you just specify this slice. And you must be careful that on the left side the slice is the same size and on the right size. And yeah, we see that is because we use the len of the rest. Yeah. Okay, and now that all that is the left is basically the same as we do above to convert this to 64 bytes, 64-bit integer. So it's same thing, but here you will of course use this new static array, and this is the same. And also here we will basically mutate this this age and using the XOR. So here, so yeah, okay, and in the end you have the you have this wrapping. So to multiply with some big constant, and yeah, so here it is the block that we cover this leftover bytes. So basically we construct this static array, copy these bytes and convert to 64-bit integer and multiply with some constants. and yeah, you can see what is left. And that's, yeah, so all that is now left to do is to perform this arithmetic before we uh, return the results from the function. So yeah, so this and that's all. That's yeah, we implemented this function using iterators, and all that is now left first to verify is it working correctly. So that we'll be doing next. Okay, so yeah, so to check we will use the same these assertion tests. I will just copy this and I will use the new function. So here, okay, and now we will use the new implementation here. Okay, and we will run. So we hear that we can yeah, all assertion went correct. Okay, so that means that yeah, this function also return correct values. And now we will go to the benchmarks. For benchmark routines, I will add small warm-up routine. We will call 10,000 times each of these method, and we will do this so because, as you know, processors are running in variable frequencies, and with this we will raise the frequency up, and results will be more consistent when we start measuring. Here I will just call this routine, and I will print the results and these two results must be the same so that we know that both of them are working exactly the same. So I will run this, and we see that we just got the same numbers here. Now I will add two benchmark routines. For each method I have a special benchmark routine. So we will call each of these methods that we implement 1,000,000 times, and we will see which one will perform faster. Okay, I already prepared the code for measuring. So yeah, so here we see that we call each of these and we measure how long it took to execute. Okay, I need to import this from time module. This. Okay, yeah, and yeah, now we are ready to measure to see which one will be faster. So I will just run the code and we see the results. So we see here that our iterator version is much slower than this, but as you know, we run this from the Visual Studio Code, and we run this in debug mode, and yeah, I expect to be slower in debug mode because we have lots of these calls that I expect when we do release mode that will be inlining these or lots of these calls, so I expect much different results when we do this in release mode. So we will do this now, and we will do this. So we will write command cargo run, and then to run in release mode to see now, and yeah, and now we see different results. So even our version is a little faster, as you see, but yeah, they are too close, so I will call that they are perform exactly the same basically, as we can yeah, we see they're very close to each other. But this was yeah, benchmark on the small small byte array, and now we will add another benchmark where we'll increase this byte array. Okay, so here are two new benchmark routines. We increase so that the size of this static array is more than 500 in bytes, and also we call it a million times each of this method, and we can just change so that we call this new benchmark, and we will do this in release mode. And yeah, we can see the results here, and we can clearly see that our iterator version is much faster than this this non-iterator version. And yeah, and we see that results are pretty much consistent. We can repeat this as many times as you like. Yeah. All that is left now is to test these benchmarks against the C++ version. So here we have Visual Studio. I just copy and paste this code that I show you in beginning of this video. I didn't modify anything, so this is this C version here, and I'll also implement this benchmark and this warm up routine, and they are basically exactly the same as the Rust versions here. Also, as you see, we are building in release mode, so just to make sure, so solution release mode. And yeah, and here we have these benchmarks the same as for the Rust. We call this million times, and yeah, and we have this for smaller array and for this bigger array. Okay, here is command prompt, and here is this program that we built, and now we can run to see the results in C++. And as you can see here, for the, if you recall, for the smaller data byte array, we see that C++ is a little slower, and for this bigger array is they are basically the same. So we can now repeat multiple times to see this effect. So it seems that it is that Rust is fast as C++ or C as you like. And also you can see that you can write performance, you can use the iterators in these performance critical loops. Okay, and that's all for this video. Bye.